Welcome to AQA A-Level Physics, Particles and Radiation, Stable and Unstable Nuclei. You should be familiar with the model of the atomic nucleus from GCSE. I'm going to draw an alpha particle here, or a helium nucleus, with 2 protons and 2 neutrons. Now there is one problem with the nuclear model we give at GCSE, and that's the fact that you're taught that 2 like poles repel from each other, but the protons, which are both positive, in this case, stick together quite packed. And that's because there's a force that you don't get told about. Let's start off with saying they're far away. Yes, much like GCSE, what you would expect is the electrostatic force, or the electromagnetic force, is very strong and it repels them. However, if they get closer together, then yes, there's still going to be the strong electromagnetic force with repulsive behaviours, but there's also going to be the strong force. Now there's a subatomic particle we call the gluon, and it's massless and it travels at the speed of light. There's some things you should know about it. But it carries the strong force, and in this case the strong force is pulling the protons together. Now this happens at ranges below 3 femtometers. I'm going to rub that out, that's a bit small. 3 femtometers. Remembering femto is 1 times 10 to the minus 15, as you saw in SI units and prefixes. Now there's one more thing to add to this, and that's the fact that if this was true, and only this was true, then the protons would continue accelerating towards each other forever until they were at the same point and became a singularity. Now we don't like that, and that's not what happens if they get very, very close. Of ranges of 0.5 femtometers, then we have still the electromagnetic force repulsing, but also the strong force now acts as a repulsive force. And in between these ranges is where the distance of the subatomic particles and the protons in the nucleus is going to lie. Now we also have to cover radiation. You should be familiar with alpha radiation. With the alpha particle, it's just a helium nuclei. Many things decay by it, but there's also something else. There's beta decay, and beta decay is a bit more complicated. When a neutron decays into a proton and an electron minus, this electron minus is the beta particle. We can sometimes write it, and in fact we normally write it like that, which actually I'm going to write, because it is a beta particle. It's a high speed electron. Now in physics, much like chemistry, we have to balance things like quantities. We have to balance quantities. For example, one is charge. We have to balance charge. Neutrons have 0, protons have +1, and beta have -1. So here it's balanced. We also have to balance the baryon numbers. We'll come on to this later on in the module, but now we just need to know that neutrons and protons are both baryons, and a beta particle is a lepton. Baryon number is balanced, and speaking of leptons, the last thing we have to balance is the lepton number. These 2 are baryons, they're not leptons, and the beta particle is a lepton. But as you will notice, the lepton number is not balanced, and so there's a problem. And this led us to theorise about the neutrino. Now, a neutrino is an extra particle produced in this decay. And we can find out some properties from this, because we have to balance the equation. It can't have any charge, it can't be a baryon, and it must have a -1 lepton number. And in fact, what actually is produced is a electron neutrino, or in this case, a anti-electron neutrino. We'll come on to more of what anti means in standard model, but electron neutrino, or just a neutrino. Now, neutrinos are very, very small particles. There's billions flying through the Earth every second, and we can't detect them. They're very small. They react with very little, and yeah, we can also write it in the other direction. At GCSE, because I knew about this, I constantly got confused on which way was which. However, I finally learnt it, and in this case, what is produced is a beta particle plus, or an electron plus, which is the antimatter version of the electron, or so an electron with a positive charge, or what we call a positron. Quite simple. And in this case, we can write charge baryon lepton, charge +1, +1, 0, baryon 1, 1, 0, lepton 0, 0, 1. Actually, that's a -1. Now, so we can find what particle do we have? Well, it must have 0 charge, 0 baryon, so it's not a baryon, and a +1 lepton number. Now, when we make a particle anti, it essentially just flips the sign, and so what it actually just is an electron neutrino. Because if we flip this, we get that. We get a positron and a normal electron neutrino if it happens in the other way. That concludes today's video. If you want to read more about things like this, I suggest looking up cloud chambers. I saw one at the Open University on display. They're quite cool things. Anyway, hope you learned something. Goodbye.